Today we want to look at a new technique, trigonometric substitution. I like to alternate technique and then ideas, technique and application, technique and application. And our technique for the week is trigonometric substitution. We've got integration by substitution. We've got integration by parts. And our third big one, trigonometric substitution. It's like substitution plus, substitution sport mode. So here's the idea. We're going to trade our x integrals for theta integrals. And we're going to turn our integrals into products of powers of trig functions. So we're going to integrate. Well, let's just describe what's going on. We're going to start with an integral of f of x dx. So we have this integral in x. Just like any substitution method, we're going to trade our x integrals, our x integral for another variable. That means all x have to be replaced. So what we do is we make our trigonometric substitution. We look at, we do trigonometric substitution when the function we're trying to integrate has a certain piece in it. So the substitution goes like this. We're looking for an a squared minus x squared we're looking for an a squared plus x squared. Or we're looking for an x squared minus a squared. These are the things that we're looking for. So we're looking for a function, that function somehow involves, let's say, 1 plus x squared. Or the square root of 4 minus x squared. That's an indication that we could do a trigonometric substitution. Doesn't always mean that we're definitely going to do a trig sub. It just means that that we can. Each of these three have a named case, or a named case. So this first one, a squared minus x squared, this is the sine case. A squared plus x squared is the tangent case. X squared minus a squared is the secant case. This is the transformation that we're doing. This is the substitution that we're going to make. A sine, a tangent, or a secant. Once we do that, once we make the substitution, our integral will be in terms of theta. I haven't told you what the substitutions were, so don't worry about what the substitutions are. So we turn our integral into a theta integral. This theta integral will be a product of powers of trig functions. So this theta integral will be a product of powers of trig functions. And this is the one that we're going to integrate. So we'll have some antiderivative in theta. But this problem was not originally an x problem, or a theta problem. It was originally an x problem. So we have to translate our theta integral back to x. So that is how we get from the integral of f of x dx to capital of x plus c, the antiderivative. We go through this integral and do our actual integration in theta. It's one of the three great tricks of mathematics. Multiply by 1, add 0, change the derivative. So this first step is where we do the trig sub. That gets us to a theta integral that we integrate. And then we have to undo our trigonometric substitution. So let's talk about what the substitutions are. So we have three cases: the sine, the tangent, and the secant case. So the sine case is when you see something like a squared minus x squared. If your function f of x involves a squared minus x squared, then you can do the substitution x equals a sine theta. So if we had 1 minus x squared, then we just substitute sine theta. If we had 9 minus x squared, then we substitute 3 sine theta. If it said 7 minus x squared, then we'd be like, oh, you're a dick. But then we make the substitution x equals square root of 7 times the sine of theta. Now, when we make the substitution, I can't just say x is equal to theta. I have to also trade out my dx. So this is going to include dx is a cosine theta. D theta. That's where the dx turns into a d theta. And this is why you have the sine case and not the tangent, or sorry, not the cosine case, because the derivative of sine is positive cosine. The other piece of information that we need here is that 1 minus sine squared is cosine squared. Now, if we think back to the same crazy things we did with substitution, this is an important part. 1 minus sine squared, 2 terms, gets replaced with cosine squared, 1 term. Remember the integrals where we had, say, x times the square root of 1 plus x. That square root of 1 plus x was really inconvenient because that 1 plus x had 2 terms in it. And I can't distribute the square roots and exponents over terms. Exponents do not distribute over terms. And so if I have a power of 1 minus sine squared, and I can write that as a power of cosine squared, I can just write that as a power of cosine, and that's better. Our other cases are the tangent case, which is for a squared plus x squared. And we make the substitution, x equals a tangent theta. So if x is a tangent theta, then dx is a times the secant squared theta d theta. The other piece of information that we'll need here is that 1 plus tangent squared is secant squared. Once again, that's the theme in trigonometric substitution. We take two terms and one term. Term Thunderdome. Two terms enter, one term leaves. No one's seen that movie. I don't know why I reference it all the time. And then our third case is the secant case. Secant case is for x squared minus a squared. Notice I don't have to reverse the order with tangent because it's plus. X squared plus a squared is the same as a squared plus x squared. But a squared minus x squared and x squared minus a squared are opposites. So we have two different substitutions. For the secant case, we make the substitution x equals a secant theta. Derivative of secant is secant tangent. So the dx in this case is going to be a times the secant theta tangent theta, d theta. The other thing that we're going to need here, if you look at the pattern that we've established so far, since it's a squared minus x squared meant we're substituting sine, and 1 minus sine squared is cosine squared. X squared plus a squared, we're substituting tangent, and 1 plus tangent squared is secant squared. So here, I'm looking at x squared minus a squared. I'm making the substitution secant, and what's going to be relevant here is that secant squared minus 1 is tangent squared. The important thing here is that we can make two terms and drop them into one term. But it's not always a product of power straight functions because I just remembered the first example that I'm going to do. But notice that there's three big steps here. Do the trig substitution to get your theta integral. Integrate your theta integral to get your theta antiderivative. Undo the trigonometric substitution to get back to your x antiderivative. All right. Any questions before we do an example? As usual, when we're looking at a new technique, I want to apply it to something that I already know to see if it's backwards compatible, because it has to be. That's just the way things have to go. Let's do an example with a function that we already know. All right, sneak attack. I didn't actually pick one that you already know. But I picked something adjacent to one that you already know. Integral of 1 over 1 plus x squared is arctangent x. That we know. So this is based on so sneak attack. Not exactly one that we already know, but it's based on one that we already know. Let's take a step forward if we can. So the first thing we notice is that we've got an a squared plus x squared. The a squared plus x squared indicates that this is the tangent case. So first, we look at this 25 minus x squared. And we recognize this is tangent case with a equals 5. Now, this is based just on this denominator. It's not the 1 over. This could have been sitting in the square roots, all kinds of things. It's just the fact that I see this 25 minus x squared. That's what's saying tangent case. So that means I make the substitution x equals 5 tangent theta. That means I also need to make the substitution dx is 5 times secant squared theta, d theta. The other thing that we're going to need is that 1 plus tangent squared is secant squared, but we don't need that yet. Here are the parts. Now I just need to make my substitutions. My integral will be the integral of 1 over 25 plus 5 secant squared theta. X is 5 tangent theta squared. The dx gets replaced with 5 times secant squared theta d theta. So we're not doing the substitution and thinking of it as an anti-chain rule. We're not looking for the dx somewhere already there. We're just trading our x's for thetas. Any questions? That 25 plus 5 tangent theta, that should be squared. That is where the thing happened. This is the reason that we did this. 25 plus 5 tangent, I'm gonna write it as saying it seemed to be incapable. There's gonna be 25 plus 25 tangent squared theta. We can factor out the 25 because I wanna look at the 1 plus tangent squared theta. And this is the thing that we wanted. 1 plus tangent squared is secant squared. This right here is the reason that we did trig sub and did this tangent substitution. These two terms become one term. That is what is supposed to happen. This is the point. And this will get us to our our theta integral. So now our integral, this 25 plus the square of 5 tangent theta is getting replaced with 25 secant squared theta. Our d theta, or sorry, our dx is still 5 secant squared theta d theta. Now all we need to do is simplify some stuff, and then we'll have our theta integral. Here, 5 over 25 cancels out, leaving a 1/5. Secant squared divided by secant squared is 1. We have done the trig sum, and now we are at our theta integral. So we start with the x integral. Now we're at the theta integral. We are here in the process. Any questions? I know I'd promised you product powers trig functions, but then I remembered I was going to do this example and it ends up being 1. Yes. I just wanted to indicate that the secants have canceled out, but I always like to factor my constants out. So mostly personal habit. That being in my trig Cal 2 class, you'll get infected with. After this class, you won't be able to say the word diverges, because you'll start pronouncing it diverges, because we spend half the semester going diverges. And you'll be like, oh, why we say it so weird? It's because we're trying to decide converges versus diverges. And so we like emphasize the die. Plus, America, emphasize the die. You know what I mean? Now we're at the theta integral. We integrate this to find the theta antiderivative. The integral of 1 d theta is equal to, so I have 1/5 theta plus c. Now we've done that step where we integrate, and we're at the theta antiderivative. Now we are here. So the last thing to do is to reverse the trigonometric substitution to get back to x. So what we notice is that we originally said x is 5 tangent theta. So remember that we said, we started this whole process by saying that x is equal to 5 tangent theta. All I have to do is replace theta. So I'm going to solve this for theta. We can divide by 5 and then do tangent inverse. So theta is going to be tangent inverse of x over 5. So our 1/5 theta plus c, I can write as 1/5 arctangent of x over 5. And here we are at the x antiderivative. We already knew this, which is why I picked this one to do first. Pick one that we already know. So there are the 4 stages. So I usually refer to them as the x integral. The next stage is the theta integral. Then we integrate to get to the theta antiderivative. And then we undo the trigonometric substitution to get back to the x antiderivative. The way I phrase that now is by saying we undo the trigonometric substitution. I used to say we go back to our x, but you shouldn't do that. Their x is for a reason, so don't go back. So there are 4 stops, so we've got 3 different stages. Stage 1, do the trig sub. That takes you from the x integral to the theta integral. Step 2, integrate the theta integral to get the theta antiderivative. Step 3, undo the trig sub to get from your theta antiderivative back to your x antiderivative. Questions? Yes. Yes. So I looked at what happens to theta to turn it into x. We do the tangent and then we multiply by 5. So we need to undo those things in reverse order. So first, if x is equal to 5 tangent theta, then x over 5 is tangent theta. So just divide by 5 first. And then if tangent theta is x over 5, we do the inverse. We write this as the inverse. Arctangent is just the inverse of tangent. If your equations are always, if you're still in the mindset of solving equations is doing the same thing to both sides, then find the inverse tangent of both sides. Divide both sides by 5, find the inverse tangent of both sides. That's our usual way into solving equations. Before we think more in terms of doing inverse operations in reverse. Questions? How's everybody okay? Everybody looks stunned. You're like, oh, it's been a 4-day weekend. You should do something easier. And I'm like, oh no. We're going straight to 10-meter platform. We're just going to skip right by 1 meter and 3 meter and 5 meter, just go right to the top. Let's jump off of that. If you're worried about this, remember, you only need to have this skill until the end of the semester. At that point, you're just going to use machines to find your antiderivatives. And hopefully, the training will take. You don't have to remember. The only reason I remember is because I do this class a lot. That's all. Normally, when we're integrating a rational or a radical function, something with a denominator, and the numerator is a 1, we like to save space by putting the dx just on top. So we're always thinking of the dx as being just a factor in our integral. So just remove the dx on top. Makes it more compact. So we look at this one and we see this 25 minus x squared. And so that tells us this is sine case. Still with a equals 5. So we're going to make the substitution x equals 5 sine theta. That will take care of the x. But I also have to find dx because the dx needs to turn into a d theta. Dx is 5 cosine theta d theta. We've identified our case. We've figured out how we're going to make the substitution. So now we substitute. Dx gets replaced with, well, let's center it. The x becomes 5 sine theta, so 25 minus 5 sine theta squared. And the dx gets replaced with 5 cosine theta d theta. After we make our substitution, this is when the trig sub thing happens. 2 terms enter, 1 term leaves. And we simplify this square root of 25 minus 5 sine squared. Let's just grab the inside of that. It's 25 minus 25 sine squared theta. So it's 25 times 1 minus sine squared theta. And 1 minus sine squared is cosine squared. 2 terms combined into one, the point of the trigonometric substitution. After the thing happens, now we're going to have to simplify our integral. So I have the square roots of all this stuff inside became 25 cosine squared. Now we can simplify to our theta, find out what our theta integral is. Now in the numerator, we've just got 5 cosine theta. And in the, oops, green though. And the denominator is the square root of 25 cosine squared theta. So that we're going to simplify to 5 cosine theta. So we'll just apply the square root. Raises an important question. Should we be worried about the plus minus business? And like, yeah, but not right now. Mostly because it's written with a radical, and that means the principal square root, the positive one. Now look at what happens to our integral. The 5's cancel out and the cosines cancel out. So our theta integral is just 1 d theta. Everything cancels. So we've done the trig sub. We've gone from our x integral to our theta integral. Step 2, integrate your theta integral. So the integral of 1 d theta is theta plus c. There's our theta antiderivative. Now we need to undo the trig sub and go back to our, to find our x antiderivative. Since x is 5 sine theta, theta will be arc sine x over 5. I like to pick the 2 easiest examples of trigonometric substitution and do those in class so that you're left with all the more difficult ones. You're welcome. I know y'all like a challenge. That's why you signed up for single variable calculus. Now let's just use one variable for everything. Any questions? Comments? Paul. So today we want to get the big idea. X integral, trig sub into theta integral. Integrate. It's usually much more trouble than it is here. And then the last part is undo the trig sub. Tomorrow we need to look at some complications for undoing that trig sub. And I'm going to look at complications for the integrating, or for integrating the theta integral. But this is the big idea. X integral, trig sub to theta integral. Integrate to theta antiderivative. Undo the trig sub to get back to your x antiderivative. And I structured it this way. I drew this picture because this is an important way to describe things. This is what we do this a lot. In linear algebra, start here, multiply by P inverse, multiply by D, multiply by P. Translate. When we're first learning a language, we get the question in Spanish, we translate it into English, we compose the answer in English, we translate back to Spanish. That's not how conversation should go. That introduces a significant amount of lag, but when we're learning, that's what's happening. And when someone is multilingual, that happens so quickly, it just becomes this. You go directly from one to the other. Any questions? That's what we call fluency. When you're just doing this, you're not going through this. Students are like, oh, what? Oh, yeah. So I'll say this. Now, how do I say that? Oh, yeah. Then they say that. But fluency happens when you skip this process. You just go right over it. That's all we want, fluency in math. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.